So first you put a little water in, and you wait on top of the burner to wait until smoke starts coming out of the can. So when the smoke starts coming out of the top, you immediately turn off the burner and place it immediately into the ice cold water.
Science rules.
So we have dry ice into the thing, we have water, we have a soapy rag, and we're adding more dry ice to get more of an effect. And then after adding more dry ice, you take the soapy rag and you put it across, you roll it up and put it across the top of the bowl to make it a ball.
When the soap gets into the water with the dry ice, it creates bubbles, lots of bubbles. And inside the bubbles comes gas, carbon dioxide. Science rules.
So first you take ivory soap and put it on a plate and stick it in the microwave for a minute. So y'all went on a field trip and y'all tell me what the experiments y'all did. What is it?
The fresh can, the dry ice bubble, and the ice.
And can y'all guess what each thing changed in each experiment? Like temperature, volume, and pressure wise?
Dry ice
and ivory soap was temperature.
So like a fresh can, temperature and pressure. So you went from a hot, steaming hot can with a little water in it to put it in the ice cold pressure can. So it went from temperature from very hot to cold to the pressure to the pressure can, right? And then the dry ice, all three of them, all three changed because the dry ice made the water cold from room temperature to very cold. The pressure changed because the bubble started to form, so it was expanding, and the volume made the bubble rise, right? And then the last one, the ivory soap. So the soap was in room temperature. You stuck it in the microwave, and all the molecules started to expand, making it hot. So that's why the soap expanded, right?
So here are some of your equations. You have your equation for Charles' law, which is volume 1 over T1 equals volume 2 over T2. And if you have a bottle containing 50 milliliters of oxygen at 300 degrees Kelvin, what is the new volume at 760 degrees Kelvin? Then it's giving you your first volume, and then it's giving you your temperature, and then it's also giving you your second temperature, but you don't have the second volume. So what you would need to do is you would need to put 50, which is your volume 1, over 300, which is your temperature 1, set it equal to x, because that's what you're trying to find, and then you would set that over 763, because that's your second temperature, and once you cross multiply your 50 and your 763, and then divide it by 300, you would get your volume 2, which is 127.16 milliliters. Okay, here's another one of your equations. It's your combined gas law, which would be P1 times V1 over T1 equals P2 times V2 over T2. And if your gas pressure is 20 atm, your volume is 26 liters, and your temperature is 260 Kelvin, and I raise the pressure to 24 atm and the temperature to 300, what is the new volume? So you already have your 20 atm, which would be your pressure, and you would multiply that by your 26 liters, which is your volume, and you would put that over your temperature, which would be your 260 Kelvin, and you would set that equal to your 24, which would be your second pressure, multiply that times your V2, which you're trying to find, over 300, which is your new temperature. And you would then cross multiply and then divide, and you will then get your V2, which is 18.77 milliliters. Your last equation would be your ideal gas law, which is PIV nert. So your pressure, your volume, set it at equal to your moles times your constant times your temperature. So if you have 8.8 liters of gas contained in a 4.2 atm and 48 degrees Celsius, how many moles are present? So you would have your 4.2 would be your pressure multiplied by your 8.8 liters, set that equal to N, which is your moles, and you don't know that, so you then multiply by your constant, which would be 0.0823, and then you will multiply that by your temperature. Now, your temperature would not be 48 degrees because that's in Celsius, so you must add 273 to transfer it to kelvins, which would get you the new answer of 321. And once you do that, you will get 36.96 equals N times 26.41, and you would divide both sides by 26.41 in order to get your answer in moles of 1.39.
Hey, it's Destiny here with your real world examples, and one real world example is, you wouldn't think about it, but it's a ping pong ball. So, who doesn't love ping pong? Say that you have a ping pong ball and you and your friend are playing and you hit the ball too hard. Now there's a dent in the ball and you can't use it. So you can simply take a saucepan and you can put it on the stove, and then you can put water in the saucepan. Then you take the ping pong ball and put it inside the pan and let the water heat up. Once the water starts to heat up, it will simply start to heat up the molecules inside the ball, making them move faster, and then the molecules will start to expand into their fullest potential, and then popping the dent outside the ping pong ball. Another real world example using Gay-Lussac's law is a gun that uses temperature and pressure. The gunpowder begins to burn, creating a large amount of heated gas, making the molecules move faster and collide more often. Then the high pressure then forces the bullet out of the barrel of the gun. My last real world example is Boyle's law, using pressure and volume. Generally, when opening a bottle of soda, we know to open it slowly, releasing the gas. When a bottle of soda is filled, it is also pressurized, much like an aerosol can. When you open it, the gas is released, decreasing the pressure and increasing the volume.